Yeah. Don't worry, Rajko, you don't need immediately start talking, right? But we want to be prepared. So are you ready?
Yeah.
Very good.
I'm ready.
It's a great pleasure to invite you again to our discrete math seminar. And today our speaker is Rajko Nenadov, who used to be in Zurich and then in Australia and then again in Zurich. And now he again moved to the other side of the world, New Zealand. And he will talk about hypergraph containers using the second moment method. Please, Rajko.
Thank you, Benny. Thank you for inviting me to give a talk at the seminar. So unlike most of the previous talks in the seminar, which focused on the recent breakthrough, I'm going to talk about a new take on a slightly older breakthrough, right? But it was a big breakthrough. So let me spend a few minutes telling you a bit about hypergraph containers. And then I will not use the word hypergraph containers until the very last minute of my talk. So hypergraph containers were published in 2010, I think around May, June, by two independent groups of authors, Balogh, Morris, and Samotij, and independently Saxton and Thomason. And hypergraph containers are one of the biggest kind of developments in probabilistic combinatorics and combinatorics in general in the last 15 years. I read their papers many times, and one thing that was always bothering me was that I could not convince myself why these things, why these things are natural. Like why I should not be surprised that these theorems, that the statements of these theorems are true. And so the last couple of years, I found a different proof of the same of these hypergraph containers, and that's what I want to tell you about. So if you know what hypergraph containers are, then what I hope you'll get out of this talk is maybe a different view on these statements. If you don't know anything about hypergraph containers, then hopefully by the end of the talk you'll find the final statement to be actually very natural, very motivated. So as I said, I will not mention the word hypergraph containers until the end of the talk. So even if you know what they are, just forget about them. Okay, so the first problem I want to consider is the following. So given a k-uniform hypergraph H and some parameter P, which is a real number between 0 and 1, we're going to form a set SP, so a subset of vertices, and we're going to form it in the following way. So for each vertex of H, I'm going to toss a coin, and with probability P, I take that vertex, and with probability 1 minus P, I don't, and I do this independently across all the vertices. Now, the question I'm asking is, what's the probability that this set SP is independent in H? And this set SP is what we called a binomial random subset. So that's the general question, and let's look at a couple of examples just to convince you that this rather abstract question encodes many interesting cases. So, for example, we can take our hypergraph H to be a hypergraph of triangles in the complete graph on n vertices. So now I'm going to form a hypergraph as follows. The edges of my hypergraph, of my complete graph n on n vertices are going to be vertices of my hypergraph. So therefore, I have n choose too many vertices. And 3 vertices in this hypergraph form a hyperedge. So it's a 3-uniform hypergraph. They form a hyperedge if the corresponding 3 edges in Kn form a triangle. Okay. So the number of hyperedges in this Tn is the same as the number of triangles in Kn, which is n choose 3. Now, if you look at a standard Erdős-Rényi random graph, GMP, right, which is formed by starting with Kn, and then for each edge tossing a coin, which with probability P tells us to keep that edge, then we have the following. The probability the triangle does not appear in GMP is the same as the probability that my binomial random subset SP is independent in Tn, in this hypergraph that I've just defined, right? And the question of where the triangle appears in GMP or any other fixed small subgraph appears in GMP, well, it's a standard, of a classical question in probabilistic combinatorics. So that's one example. A different one, which might be even a bit easier to grasp, is that I'm going to form a hypergraph AN, which is a hypergraph of three-term arithmetic progressions among the first n natural numbers. So the vertices of my hypergraphs are numbers 1 up to n, and three numbers, or three vertices, form a hyperedge if they form a three-term arithmetic progression. So every triple of the form a plus d, a plus 2d, where all three numbers are between 1 and n, forms a three-term arithmetic progression, right? And then, again, another classical question in probabilistic combinatorics is, if I look at the first n natural numbers and I pick each of them with probability p, then what's the probability that the resulting set contains three-term arithmetic progression, which in our language is the same as asking what's the probability that the corresponding set SP is independent. Good. So, using hypergraphs, one can encode many cases of interest, and get a sort of a common framework for studying them all at the same time. Okay. So, how do we approach this question of what's the probability that my set SP is independent in H? We can use, say, Chebyshev's inequality. So let me denote with X the number of hyperedges of H which are contained in SP. Well, so that's a random variable. And I can write X as X1 plus X2 plus XE of H, where what I first do is I order the edges of H however I want. And then for ith edge, I introduce indicator random variable Xi, which tells me whether this edge is present in SP, fully present in SP or not. Okay. Now, the probability that SP is independent is the same as probability that X equals 0, right? So I see no edges inside SP. Chebyshev tells us that we can upper bound this by variance divided by expectation squared, right? Now, instead of variance, I'm going to use this approximation of variance, which I'll denote by delta, which in the case where P is small, and we are working with the case that P is a little of 1, so this delta is a fairly good approximation, and a standard approximation of variance. Good. However, in this case, or in this particular setup, we have a better bound, and that's Janson's bound. Janson tells us that this is actually at most e to the minus mu square over delta, right? So you get the same ratio, but you get it in the exponent. Very good. So Janson's inequality is really the starting point of our journey towards hypergraph containers. So let's see some examples. So what does Janson tell us about the probability of triangle not appearing in GMP, or three-term arithmetic progression not appearing in a binomial random subset of the first n integers? In terms of triangles, this exponent behaves roughly like this. Before 1 over n, so when p is much smaller than 1 over n, we're not really going to see any triangles. So I just focus on what happens afterwards. When p is between 1 over n and 1 over...
This log is just this your mu, this delta over mu square, right? This thing is the exponent, right?
Yeah, there's the exponent. Yeah. So sorry. So yeah, I'm just focusing on what's in the exponent. When p is between 1 over n and 1 over square root n, this exponent behaves roughly like n cubed p cubed, which is nothing but the this is expected number of triangles in GMP. And then there is a point of change, which is at 1 over square root n, where the exponent is no longer roughly the expected number of triangles, but it becomes the expected number of edges. So up to 1 over square n, the exponent is the expected number of sampled triangles. After 1 over square root n, the exponent is the expected number of sampled edges. And we have a similar behavior in the case of preterm arithmetic progressions. So below n to the minus 2/3, we're not going to see any 3-term arithmetic progressions. Then between n to the minus 2/3 and 1 over square root n, the exponent behaves like n squared p cubed, which is the expected number of, and then past 1 over square root n, it behaves like expected number of sampled elements. Now one can ask, how good are these estimates? And it turns out that this logarithm is that the Janson gives us the correct order of the logarithm, or it gives us the correct order of the exponent. Now let me give you a very brief argument why this is the case in this upper regime. And it's for a very, very silly reason. The probability that SP is independent, we can trivially lower bound it with the probability that SP is simply an empty set, right? Which happens with probability 1 minus P to the number of elements of my hypergraph H. And throughout the talk, I will denote the number of elements of this hypergraph H with capital N, right? And that's then E to the minus P times capital N. In terms of triangles, I have order of n squared many vertices. So n squared p is the expected number of sampled elements. In terms of 3-term arithmetic progression hypergraph, I have n vertices, and then again the expected number of elements is np. Good. Now, in terms of this more general form of what Janson gives us, what happens in this upper regime is that we have this delta is roughly over np, right? And the same here. So once delta becomes of the order mu square over the expected number of sampled elements, then it's this expected number of sampled elements that governs the exponent. Good. So now let's change the question a little bit. Now, instead of picking our random subset by taking every element independently with probability p, let's pick a subset of size m uniformly at random among all subsets. And this is what we call uniform. So this is a uniform random subset. And now we can ask again the same question: what's the probability that it's Sm, a subset of my vertex set of size m, chosen uniformly at random, that it forms an independent set? we can get a good upper bound by just approximating Sm with Sp. So if we take P to be M divided by capital N, right? So M divided by the number of vertices of my hypergraph. And now I choose every vertex independent with probability P. In expectation, I have exactly M vertices. In reality, it's gonna fluctuate a little bit around it, but it's gonna be concentrated enough that I can transfer the upper bound coming from Janson's inequality. So if I just do that, then I get the same thing as before, that the probability that Sm is independent is at most e to the minus the same quantity, mu squared divided by delta. Mu square and delta are no longer, so mu is not really now the expectation, because now we have a fixed number M of vertices that we are sampling. But mu is roughly the expectation of the expected number of edges that we see inside Sm, and the same holds for delta. So again, mu and delta are good approximations for the expected number of edges and the variance on the number of edges inside Sm. And now the case that I really care about is this upper regime where delta is of order mu square over M. Right? So M is just MP, the expected number of sampled edges, if in the SP model or in the binomial random model. And in our case, now it's exactly the number of vertices we're dealing with. So in this case, where the Janson tells us that probability that Sm is independent, we can upper bound it by E, something like E to the minus M, right? E to the minus number of vertices that we are sampling. Now what about the lower bound? Well, the lower bound is now a bit of a problem, because in the case of SP, we had this trivial lower bound, where we say, well, if SP is independent, if SP is empty, then SP is independent. Now we can't do the same here, because Sm is never empty, right? Sm is always of size M, which prompts a question of, is there a different reason for the probability that SP or Sm are independent? And if you think about it, one case would be, well, if my hypergraph H has an independent set of size, say alpha n, then my sampled subset would also be independent if it lies completely within such a set. So this doesn't really make any difference in terms of when we talk about the binomial random subset, but it makes a huge difference when we talk about uniform random subset. So if I know that I have a independent set in H of size, say alpha n, then I can lower bound the probability that Sm is independent by estimating the probability that Sm is completely contained within such a set, right? Which happens roughly with probability, alpha to the MP or alpha to M. And now the problem is, well, Janson gives me the upper bound of order e to the minus MP. And here I have a lower bound of order alpha to MP. Now, if this alpha is little of 1, then these two bounds diverge. And so the question is there a different reason for my Sm being independent, or is Janson inequality just simply not accurate enough in the case of uniform random subsets? So let's look at these two examples. So in the lower regime, where in the case of triangles, so when p is less than 1 over square n, then we have that the exponent is given by the expected number of triangles. This turns out to be also correct in terms of in the uniform subset, and the same holds in the three-term arithmetic progressions. The more interesting case is what happens in this denser regime. Now, when you look at triangles, so when you look at this hypergraph of triangles, this hypergraph does have a very large independent set. Right? So take a complete graph and look at the largest bipartite subgraph of your complete graph. Take these edges and look at the vertices corresponding to these edges in our hypergraph, because these edges correspond to bipartite subgraph of Kn. They form an independent set in our hypergraph, right? And that's an independent set of size number of vertices divided by half, roughly. So in case of hypergraphs, in case of triangles, we can even take this alpha. We can take this alpha to be 1/2, right? Which gives us a lower bound of order e to the minus m, or n squared p. And we have a Janson giving us the matching upper bound. So we're happy with it. And now, really interesting thing happens in the case of three-term arithmetic progressions. Largest independent set. So the largest number of vertices of numbers from 1 to n I can take without having a three-term arithmetic progression is little of n. So that's Roth's theorem. So if I just plug in this bound, that gives me little of 1 to power of m, or e to the minus some function of e to the minus, say, omega m, so little omega m, so some function of m that keeps going away from m, whereas the Janson gives me the upper bound e to the minus m, so the two diverge, and this bound, right, this bound is not tight, and it turns out that this lower bound coming from the considering the largest independent set actually gives the correct answer. So we know that in the case of three-term arithmetic progressions, that this set Sm will be independent with probability e to the minus omega of m, as m keeps growing, right? So once m is past square root n, then the further we go, this probability will become, it will decay slower than e to the minus any constant times m. So that's a problem, because now we have cases where, so in the case of binomial random subset, Janson is always correct. In the case of uniform random subset, sometimes Janson is correct, sometimes Janson is not correct. And
all right. Can I ask you, but you're a bit hiding under the rug that you can have many independent sets, right?
I have, yes.
This can maybe correct the situation, right?
This might correct, but it's not going to. It's what turns out that it's really that just having small independent sets is already good enough. But yeah, it could be the case that I have so many that my independent sets are small, but I have so many of them that are very likely to be subset of one of them. But that turns out that's not the case. It's really that as soon as they're small, that's going to drive the probability much quicker to zero than if I had one big one. So informally, the statement that I'm looking for is, well, I want to incorporate this information about largest independent sets essentially into Janson, right? So what we are looking at is a regime where Janson would tell us the sample subset is independent with probability exponentially small in the number of sample vertices, right? So that's precisely when this delta is of order mu square over m. Now, once we let m keep growing away from this value, what I want to say really is that the size of a large independent set really governs this probability that Sm is independent, right? Because that's precisely the parameter that's one of the parameters that Janson is not taking into account, and that becomes relevant when once my sampled subset becomes sufficiently large. All right. So I want to give you a brief idea of how to prove this, and then we'll slowly wrap it up, and eventually we're going to end up with what some of you might know as hypergraph containers. All right, so how do we prove this? I want to give you the intuition of why this is true. And the most important part of this talk is to realize what happens at this point M naught. So what happens at the point where when Janson tells you that the probability will be exponentially small in the number of elements. So this point M naught, that's the point at which if I take my random subset Sm, then this subset is going to saturate many vertices of the hypergraph H in the following sense. So if this is H, and then this is my Sm. Let's assume that my hypergraph is free uniform. Then for many vertices outside of Sm, there will exist two vertices inside Sm such that these three form an edge. What this means is that if my random subset is independent, then this vertex, well, it cannot be inside Sm. Now let me, I'll go over this once again. Let me just give you a brief, let me show you an example why this is the case. So if we look at the case of triangles, then if you do the calculation or just you look at the plot I've shown you before, then the regime you're interested in is when m is bigger than n to the 3/2, or equally or equivalently when p is, let's say, bigger than 1/square root n. Then what happens is that whenever I look at some edge of my Kn, and I look at how many almost triangles sit on it. So I look at the number of triangles where this edge belongs to my set Sm, and this edge belongs to my set Sm. How many of such triangles I have sitting on a particular edge? Well, I can choose this vertex in n-2 ways. I see this with probability p, and I see this edge with probability p, and all this is independent, so I have roughly p squared. Now, if p is much bigger than 1/square, then the number of such triangles sitting on a chosen edge is at least 1, right? Which means that once my probability p is bigger than 1/square, then typically any vertex, any edge of Kn I look at, it sits on this, it sits on this almost triangle. So triangle where the other two edges are coming from the sample set Sm. And this turns out to be the case in general. So how can we make use of it? So suppose this is my set, and let's just consider this three-uniform case of a hypergraph encoding triangles. Now I'm going to generate my set Sm into rounds. I'm going to generate it Sm union.
Rajko, we don't hear you. Rajko? Okay, I think we lost the speaker. I will try to maybe.
Oh, sorry, some reason internet dropped.
Right. So are you back, Rajko? So right,
Yeah.
good.
Good. Sorry about it.
Okay, so right, so you were talking to us, right? But we hear basically this thing about edge closing the two triangles, which you wrote,
Very
and
good.
then we lost you.
Yeah, very good. Can you see me well? Can you hear me well?
Yep, we hear you well. We don't see you, but that's okay. But at least we want to see the slides, and if you write, and we will see how
Very good.
the slides. Ah, now we also see you.
Good, good. Okay, yeah. So the internet connection dropped.
Right.
Anyhow, yeah. So what I was saying, we take this set Sm prime, the little one, and then we look at all the vertices which form a hyperedge with two vertices from Sm prime. Now, if you think about this case of triangles, then well, just kind of give you an intuition why we should expect. Actually, most of the vertices should be in this bucket, right? Most of the vertices of my hypergraph should form a hyperedge with two vertices from Sm prime. Now, if this set of the remaining vertices, let's call it R, if R is less than, say, alpha n, then I get what I want, because now if Sm is, for Sm to be independent, I necessarily need that this Sm prime lives inside R, which gives me very few choices, right? That gives me the probability of that happening is roughly the size of R divided by n, and then 1 minus epsilon n, which is roughly alpha to the n. So that's the whole point. That's the whole intuition, that I reveal a small part. I look at which vertices are forbidden because of the small part, and if I can argue that that's most of the vertices, then I'm in a good shape, because now when I reveal the biggest part of my subset, random subset, for it to be independent, it really needs to sit inside this small leftover. Now, this strategy doesn't work, and doesn't work because I'm asking for something very strong. Well, what I'm asking really here is, what's the probability that the small Sm prime saturates, let's say, all but that it saturates all but some small fraction of vertices. And I'm at no point I'm using any information about independent sets in my hypergraph H. So this probability really, it cannot be too small, because if this probability is always at least, say, 1 minus alpha m, then overall I get probability which is too good to be true. Right, so this probability has to depend on the independent set of my subgraph, of my hypergraph. And estimating this probability that Sm saturates almost everything, it doesn't really seem to be any easier than the original problem. Okay. Okay, that's the first attempt. That's the general intuition. So let me give you now a slightly more accurate description of what's going on. And now the strategy is as follows. So again, I want to reveal my sampled set in rounds. But instead of having this very ambitious goal of revealing one part, saturating almost everything, and then asking for the second part to be contained in the leftover, I'm going to generate my Sm in more smaller rounds. So I'm going to generate this Sm1 union Sm2 union SML, and then I'm going to reveal the the second largest part. So L is some constant. And each of these sets SMI is roughly of size epsilon L times M. So these small sets here, they're going to have the role of this SM prime. And I'm going to do it in rounds. And here's what I'm going to do. So first I look at this SM1, and I'll look at which vertices are saturated by SM1. Okay, so I look at which vertices here form hyperedge with two vertices from SM1. Technology. Good. So I'm going to look at which vertices. Just a second. What happened?
We don't see your screen, Rajko.
Yeah. Share screen. OneNote. Give me a second. Share screen. OneNote.
Yes. Very good.
Share. Good. Sorry about it. Yeah, so we look at which vertices form a hyperedge with two other vertices from this SM1. And the previous attempt, what I was aiming for is I wanted to say that this is almost everything. Now I want something much more modest. I want to say this is something. So all I'm looking for is that this is a small fraction. Okay. Good. Now I take this and I put it aside. Now let me denote with R whatever remains. Now, if I want my my whole subset to be independent, all these other small subsets, they need to lie inside R. Now I sample my SM2, and again, inside this set R, I look at all the vertices which form hyperedge with two vertices from SM2, and I hope to get a small fraction. I delete them, and then I say now this is my set R. So what is it I'm hoping to achieve in every step? I'm hoping to achieve some constant progress. Now, this constant progress, we only have a chance of achieving it if the following happens. So in each step, we look at this subgraph induced by R. So my current set of vertices that of vertices where my sample set has to live to be independent. And now there are two things that can happen. It can happen that H of R has many edges. Many means at least a big number of edges of my hypergraph. If this is the case, then we continue, right? Because if this subgraph here, if this subgraph has many edges, then I have hope that once I take a small sample, that will saturate many vertices. And how many? Well, I hope to bound this by some function of beta. Right. The fewer edges I have inside this HR, the less vertices I can hope to saturate. But as long as this is some beta fraction of the total number of edges, I can hope to saturate some fraction of the remaining vertices, and this fraction, it will depend on the number of edges I have, right? So that's one case. The other case is if I have few edges. Few means less than beta fraction of all the edges. Then I can't really say anything. But this for us, this means that R is almost independent. If R at some point becomes almost independent, I stop. And now let me revise the statement I wanted to say here. So we wanted to say that once M becomes large, the probability of Sm being independent is governed by the largest independent set. Instead of that, what we can show is that the largest, briefly go over the argument. So we reveal the small sets Sm1, Sm2, Sm3, one at a time. Every time I reveal a set, I look at what are the vertices that are now forbidden if I want my Sm to be independent. I remove them, and I have this set R of the leftover vertices. And as long as the whole hypergraph H has many edges inside R, there is hope that if I take a small sample, then the small sample will saturate some fraction of the vertices, and then I can continue this process. I cannot continue it if H is rough. If H has no edges inside R, then I cannot hope to saturate anything further. Or slightly stronger state or weaker statement is if R has very few edges, then I cannot hope to saturate many vertices. In which case I stop, right? And this is but then I arrive in an almost independent set, which is what we were aiming for. And the crucial point here is that there is this cutoff beta. So if my number of edges is bigger than beta fraction, then I continue. And if not, then I abort, and then I have my independent set. And why I can keep this alpha to be constant? Well, it's a constant that depends on beta, and not on epsilon, and that's crucial. And that's because epsilon m over L is still large enough that I can hope to cover a fraction of vertices which only depends on beta. Now, in the first attempt, I told you what we want to show is that we want to estimate this probability that Sm prime saturates all but alpha n vertices. Now we relax that, and now we say, okay, what I want is that my little set Sm prime saturates only alpha n vertices, say. And now I want to convince you why this is a much easier task than, so covering alpha fraction is much easier task than covering 1 minus alpha fraction. And here's the argument, which is really kind of the crux of the proof, and it's really what makes this hypergraph container stick. So this is my hypergraph H, and this is my set, randomly subset. Let me call it now this Sm prime. And now here's the assumption. So I want to show that there exists a small fraction of vertices, but a positive fraction, which are saturated by this Sm prime. And here's the assumption. So suppose that Sm prime is such that it contains at least some the fraction of the expected weights of this of these almost edges. So so suppose we have at least this many edges that contain k minus 1 vertices in Sm prime. Okay. So this thing here, that's the expected number of vertices, the expected number of edges that of my H that intersect Sm prime in k minus 1 vertices. Suppose that we condition on Sm prime having at least a small fraction of this number of edges. Now let me denote with d of v the number of hyperedges in H, that V forms with k minus 1 vertices from Sm prime. And let D be a random variable dV for V chosen uniformly at random. Okay. What I want to show is that I want to show the probability that D is bigger than 0 as some small positive number, right? So if I can show that if I chose my vertex V uniformly at random, and then with probability, with some constant, small constant probability, this variable D is bigger than 0, that means that this randomly chosen vertex is forming a hyperedge with some k minus 1 vertices from Sm prime, which is precisely what I want to calculate. This means in total that I have a small fraction of all the vertices which are forbidden. So this probability tells me exactly how big this set is. Now, how I'm going to estimate this? I'm going to use Paley-Zygmunt. So Paley-Zygmunt inequality tells me that this is at least expectation square divided by expectation of D square. Right, I want to say that this is at least some small constant. And that's where the second moment comes into play. And we'll see that this condition of delta being mu square over m is precisely what's needed for this to work out. So let me briefly give you some numbers. So what's this? We assume that, and this is a big assumption, and I can say a few words why it's not such a big cheat. We assume that Sm prime contains at least this many edges intersecting it in k minus 1 vertices. So this is really just 1 over the number of vertices because I choose my vertex V at random. And then I have something like delta E of H and k minus 1 right square. Now, if you rearrange stuff, you get something like this is beta over epsilon mu square times epsilon m squared times parameter u with the parameter epsilon squared. Okay, so this is just what comes in a straightforward way from that assumption. More interesting part is how do I estimate this term? So what's this? I choose my vertex at random. I go over all vertices, and then I look at this dv squared. Now, what's dv squared? I look at vertex v, and I look at all the pairs of edges E and E prime, which contains v. So that's one way of counting it, but I can count in the other way. I can choose E and E prime, which intersect, and then I can pick one vertex inside to be v, right? So I can rewrite this as 1 over n, and then I iterate over all pairs of edges which intersect. I choose my intersecting, I choose this vertex v to be in the intersection, so I have at most k ways of doing it. Right, and then what's the probability? And now here I'm really cheating because so this expectation here goes over both Sm prime and v. So I am not fixing Sm prime and revealing Sm prime and v at the same time. What I have here is epsilon m over n, and then I need to see all the other vertices other than this fixed vertex v. They all have to appear in Sm prime. Therefore, I have this many vertices I have this many vertices that I have to choose in Sm prime, which gives me precisely this. And now what's this? If you rearrange, you get that this is roughly k over epsilon m squared times mu epsilon m squared. And that's because, actually, let me do it a bit slower. So what's this? This is, so let me take k out, it's k over n. Let me also take this -1 outside. So I have n over epsilon m. What remains is this sum. Right, but this sum here, this is exactly d of delta of epsilon m. And because epsilon m is still much bigger than m naught, I know that this is roughly the same as mu epsilon m squared over epsilon m. And then n cancels out. And what I'm left with is k times mu epsilon m squared over epsilon m. So I have this. I have something very similar here. And then when I plug both in here, what I get is, it's at least delta over k, okay, which is precisely what I wanted. So if delta was constant, then this whole thing is constant, and I really get that this covers most of the that this covers a small fraction of the vertices, and I can continue. Yeah, and this parameter delta really comes into play through the second moment. Good. So maybe it's just some out of time. Maybe just 1 minute more to wrap it up and to write the final statement, and then we can move on to questions.
We can have 5 minutes, but like 5 minutes and not more.
Okay, very good. Okay, so let me tell you what's the cheat here. So there are two cheats. First, we had this assumption, which it's a big assumption, but well, you have to trust me that that's not an issue. Much bigger issue is that here, my expectation goes over both Sm prime and V. So what I really want to say is something of the following form. So I want the probability over my Sm prime of the following event, that when I take now V uniformly at random, and I look at this expectation of D square, I want this to be upper bounded by this parameter mu of em squared divided by epsilon m squared. And I want this to hold with very, very small probability. Oh, sorry, with very, very high probability. So this is much more serious cheat than this one. And how do you prove this, and why it's plausible that I can get such a good bound? You prove this using Rudolph-Rudzinski Rudolph-Rudzinski deletion method. And the whole point why I can get such a good bound is that I'm upper bounding the expected number of copies of some overlaps of hyperedges that are contained in my set, or that intersect my set. And Rudolph-Rudzinski gives us a method of getting a good tail bounds if we are willing to remove a few elements. So that's in 1 minute why this is plausible. Okay, so let me now give you the slightly more formal theorem, and I'll finish with that. So let M naught be such that we are in the regime where Janson tells us that the probability is bounded by e to the minus number of elements sampled, maybe times some constant b. Then for every epsilon bigger than not, there exists t. Such that if my m is bigger than t times m naught, so if we are significantly far past m naught, then with probability at least 1 minus epsilon to the m. So, and I choose epsilon, and that's crucial. We have one of the following two events. So first event is that SM is not independent. And the second case is that SM is independent. And there exists some small subset f of SM, size of epsilon, which is a function of f, such that most of my SM lies inside C, and B, C is independent, right? Meaning that the number of edges of H inside C is less than epsilon times epsilon fraction of all the edges. Let me zoom it out. So this is what we really showed before. And now if you know what hypergraph containers are, you will see that modulo this probability here, this is really what the hypergraph containers tell you. So hypergraph containers are a bit stronger because there is no probability there. They tell you that this holds for every independent set. Here we sacrifice that a little bit, so we get a slightly weaker bound. But I hope that the proof is a bit more motivated and maybe a bit more systematic. Yeah, and with that, I will finish my talk. And yeah, are there any questions?
Yes, thank you, Rajko. So people can unmute. Maybe let's first thank Rajko for the talk, right? So very interesting. And so people can unmute themselves and ask questions.
So, thanks for the talk, Rajko. I have a question about this final theorem. So usually in containers, you need some assumption about the codegrees of all sets. Is that like hidden in the definition of M naught here?
Yeah, that's kind of the point that, if the talk was 2 hours, I will have time to get into it. Yeah, so you don't need the condition on every, you need an average. And this parameter delta, at this point M naught, at which Janson start to give you probability, so yeah, let me. So this condition here, in some sense, capture this condition that codegrees are good. We don't require here that all codegrees are good. We just require that, in some sense, on average, they're good. So there could be a subset which is contained in many edges. That's absolutely fine. And the price you pay is, you pay the price here.
Thanks.
You're welcome.
So Rajko, so this statement with probability, can't you because probability kind of tells you counting, can't you kind of converted to the statement which kind of gives you full containers, right? Just because basically it tells you that almost all like the sets, right? Because probability is just you count how many sets are. So they don't tell you all, but almost all, and then maybe you can somehow fix this error term, or it's really
it's clear. I can't convert it, and the reason is that I think the bottom line is that like Yuval asked, we don't have a strong condition on these codegrees. And it could be that some small subset have very bad codegrees. And it could happen that you pick some of them. Yeah, so this statement, this probability 1 minus epsilon m, it tells you that most of the subsets of size m behave well with respect to codegrees. But I cannot conclude that all of them. So if you would strengthen the requirement by not working with delta and mu, but working with the strong assumption codegrees like the original containers do, I guess then probably you can recover the full hypergraph containers. But then that was not the point. So the point was really to tie this to this upper regime where Janson inequality is sometimes correct, sometimes not, and to understand, how one can fix it, and yeah. But that epsilon really is there because some sets of size m can really behave very badly with respect to building the whole with respect to this iterative procedure.
Okay. So more questions? So if not, maybe let's thank Rajko again.
Thank you.
Yeah, we can stop recording.